I'll begin. Holy Father, we thank you for this day. Thank you for these students. Lord, I just pray you be with us today. Help us to glorify you. And we pray for the election tomorrow that America would have some common sense, Lord. In your name I pray. Amen. I should say uncommon sense, perhaps. I don't know. But one of my colleagues told me his favorite sticker was, I voted and I got some on me. Or okay, so we're in chapter 10. So our main goal here is to understand the calculus and geometry of parameterized curves, and also alongside of that we're going to look at polar coordinates at some point. So any questions before I get started? So I promised you guys a few like sort of token homework problems from last time. So here's some good practice problems. Because I don't really have any problems from the book per se from last time to give you, but here's some good potential like quiz problems or whatever. If A is equal to say 3, 7, and B is equal to 4, 5, find the angle between A and B, and also between A plus B and A minus B. That's a good problem. 2, if A dot B is equal to 10 and the angle between A and B is theta equals to 30 degrees. Given the magnitude of A is equal to 3, find the magnitude of B. That's a pretty good problem. I'll try to find it. Here's another problem. 3. If A is equal to some constant 3 and B is equal to 1, 7, given that A dot B equals to 31, find C. I mean, here's some potential homework problems. These are the problems like we worked last time. These are pretty good sort of basic problems. Basically, my point to you is you should try to understand the dot product from last lecture, okay, and its connection with the angle. That's the main thing. All right, so my focus for today, is on how to parameterize curves and what is the parameterization of a curve. All right, so let me just state it again for you. So a curve. What's a curve? This is just some set of points for our purposes in R2, all right, where the path is a function from some subset of the reals to, in our case, R2. So there's lots of different ways to describe a curve. Could be something like solution set to say x squared plus y squared equals to 10. That would be a Let me make it more fun. Let me make it 9. You know, this would be a way to describe a curve. It could be the solution set to some equation, right? My equation, the curve I'm talking about, is a circle, radius 3, centered at the origin, right? A path, on the other hand, a function, so, you know, that would be something like r of t equals to 3 cosine t, 3 sine t. This is a path. This is a path which covers that curve. So that path is called a parameterization of the curve. So let me just terminology. So this is a parameterization of the circle x squared plus y squared equals to 9. So here's the main task I want to put in front of us today. Given a curve, find its parameterization. So this is our big goal for today. So let me start out with something small. So find a path from, let's say, 1, 2 to 3, 4. All right. So let's see here. So here's the point 1, 2, let's say. Here's the point 3, 4. Very heuristic picture. I'm asking us to find a path which goes from there to there. I guess another way you could look at it is I'm asking you to parameterize this line segment, right? And I tell you what, I'm going to put a little bit more on us. I'm going to say that I want this initial point to be where t is equal to 0, and I want the final, I wrote 1 but I said 0, and I want this final point over here to be t equals to 1. Right? I'm going to show you a trick, all right? Now we could work this through, work this out any number of ways, but I really think that it's just best to learn this trick. So here it is, r of t is equal to, what we're going to do is we're going to put 1, 2 here. All right, we're going to put 1, 2 here. So if you think about it, when I put t equals to 0, right? When I put t equals to 0 in here, it doesn't matter what I put in these parentheses. T equals 0 gives you what? 1, 2, which is what I want. All right, I want r of 0, r of time 0 to be 1, 2, and I want r of time 1 to be 3, 4. All right, so if I put 1, 2 there, we've got half the job done already, right? How can I get 3, 4 to come out of that formula when I put in t equals to 1? What do I need to do? Well, if I put 3, 4 there, we're almost done, right? If I put 3, 4 here, that's pretty good. If I just put 3, 4 here, then I put t equals to 1, I've got my 3, 4, right? But what's the trouble? I've still got the 1, 2, right? So to get rid of that, I just subtract it. So this right here is, this is actually the direction vector 2, 2 as it happens. So like this purple vector, for what it's worth, actually is that green, is 2, 2. Anyway, so there it is. So we've got, let me clean it up here a little bit. So that's, this again, this works out to 2, 2. So that's 1 plus 2t, comma 2 plus 2t for 0 less than or equal to t less than or equal to 1. And there you go. That is the path which parametrizes that line segment in vector form. So this is the vector parameterization. So if I wanted scalar parametric equations, what would the corresponding scalar parametric equations be? In other words, we get x is equal to 1 plus 2t, and y is equal to 2 plus 2t, 0 less than or equal to t less than or equal to 1. Here you go. These are the scalar parametric equations of this line segment. I really don't like the term equations, even though it's customary, because it doesn't emphasize what parameterizations really are. Parameterizations are functions. It's the image of the function, which is the path. In contrast, right, the curve, x squared plus y squared equals to 9, the idea is that the solution set to that equation is the curve, right? Here I'm saying for each time you stick in, you get a point on the path, right? It's exactly backwards of the other idea. Anyway, any questions about this example? If I ask you to parameterize a line segment between 2 points, you can do it, right? Is there anything special about 1, 2, 3, 4 here? There is not, right? Yeah. What if I said, find a parameterization, here, let me just tweak this a bit. Example 2. Find path from 1, 2 to 3, 4, which takes t ranging from t equals to 0 to t equals to 3. How would you do that? So, I mean, fill in the parentheses. You want something that gives you 1, 2 when you put t equal to 0, right? And you want it to be giving you 1, 2 plus 2, 2 when t equals to 3. So what do you do there? You don't put t there. Instead, you put what? T over 3, right? Basically, just take the same linear path and just slow it down, right? So once you understand this, going from 0 to 1 to get from one point to the other, you can twist it and make it take more time or less time, right? What if you wanted to go in half a second, assuming t is time? 2t, right? Yeah. Suppose I wanted it to take from time 3 to time 4. Let's say at t equals to 3 and 3, 4 at t equals to, let me make it 5. So I'm just basically messing with what goes in here, right? So you want it to be and I kind of have to think about this one a little bit. I mean, I guess I want t minus 3, right? That's pretty good, because when I put in t equals to 3, I get 1, 2, right? But it's not very good, because when I put in t equals 5, I get what there? I get 2, right? When I get t equals to 5, I want 1, 2 plus 2, 2, because I know that gives me 1. It gives me 3, 4. So I need to take this and do what? I think if I divide that by 2, it should work, right? Does that make sense? Does that work? If you plug in t equals to 3, we get 1, 2. If you plug in t equals to 5, we get 5 minus 3, which is 2, divided by 2, which is 1. So then I get back to 1, 2 plus 2, 2, which is 3, 4. Yeah. So there you go. Yep. Oh, no, that was stretching. That wasn't a question. Okay. Just checking. All right, I'm just about out of twists on the line. I mean, you could do other weirder stuff, like you could look for a non-even like parameterization. You could look for something weirder, like here I could do this. If I look at r of t equal to 1, 2 plus t squared times 2, 2. Oh man, my back is screwy. Not cool. Look at that. Let me call this example, let me call this R4 versus this one that we did to start with. Let me call this R1. Okay. I'd like to compare them. Does this also give you a parameterization that goes between the 2 points and is on the line segment? I mean, when I plug in, put in time equal to 0, I get 1, 2. When I put in time equal to 1, I get, again, 2, 3, 4. And I guess, you know, the question then is, how do I know that this stays on the line? Well, I would argue that that's geometrically clear, because what you're doing with this formula is you're starting out at 1, 2, right? And then you're just adding copies of this 2, 2 vector rescaled, right? I mean, this doesn't change the direction of 2, 2. It's always in that direction, and you're just adding different amounts of it until you get over to 3, 4. Well, so what's the difference between R4 and R1? It's all about velocity, right? So like, if you calculate V1, which would be dr1 dt, what do you get here? If you differentiate this, we get what? We get 2, right? So we've got a constant velocity. This is a constant velocity path. In contrast, this weird example I just made up, if you calculate the velocity of the 4 path, dr4 dt, what do you get? Here, I'll write out a step for you. That's 1 plus 2t squared, comma 2 plus 2t squared. When you differentiate that, what do you get? Yeah, 4t. So this thing is kind of wacky. It starts out with 0 velocity at time 0, right? And then the velocity gets larger and larger and larger until you get all the way to t equals, by t equals to 1, your velocity is 4, 4. Right? So the velocity is not constant in this path. So like the first path, you're going from the point 1, 2 to the point 3, 4, sort of at a uniform rate, like, right? So like the first path is something like like that. The second path, I mean the fourth path is more like this. I can't do it, but I mean it's getting faster and faster as you go, right? So here are these 4 examples. These are all parameterizations of the same curve. The curve is the line segment from 1, 2 to 3, 4. These are 4 separate parameterizations, right? So there are many, many different ways to get, to cover one path, cover one curve using different paths. So this task I've stated at the beginning is an ambiguous task, right? Given a curve, find its parameterization. So usually, because I don't like grading infinitely many answers, I'll add some baggage, right? Like, find a parameterization as we usually do, or something like that. Okay? Oh, any questions before I erase? Okay. So let's talk about standard curves. All right, so what I'm going to do here is I'm going to make a table for you. And we're going to fill in this table with some standard parameterizations. All right. And so here's a, first of all, if I have x minus x1 squared plus y minus y1 squared, and this is equal to r squared. So this is what? This is a circle, right? Circle, what's the center? The center at x1, y1, and the radius is what? R, right? So here's the curve. Here's a possible parameterization. So I'm gonna write the scalar parameterizations here. I think I've done enough with vector parameterizations for the moment. Let me kind of focus more on the scalar terminology here for a bit. That's more where your book is. So here it is. What you do, if you want the whole circle, right, you just let x equal to x1 plus r cosine t, and you let y equal to y1 plus r sine t. And then however much of the circle you want. I mean, it depends on what you want to do, right? Like, if I want the whole circle, I do 0 less than or equal to t less than or equal to 2 pi, right? What if I just wanted the upper half of the circle? You know, what if I just wanted you might have to zoom in on this, Nathan. What if I just wanted like this piece of the circle, right? Then what should I do? I just limit the parameter domain, right? I do 0 less than or equal to t less than or equal to pi. And you can play these games to select any little part of the circle you want, right? You can do other more interesting things too, right? Like you could say, I want a path which covers the circle 2 times. Then what do? You just let it range from 0 to 4 pi or something like that, right? Now, why is this a parameterization? What does it take for the thing in purple to be a parameterization? What does that mean, pragmatically speaking? All it means, really, guys, is that if I plug in these formulas, right, if I plug these formulas up into the equation which defines the curve, they work. Right? Can you see why that would be true? If I take x minus x1, what do I get? I get r cosine t, right? If I take y minus y1, I get what? I get r sine t. So if I plug those up into here, I get r cosine squared plus r sine squared, right? R sine t squared. So I get cosine squared plus sine squared, which is 1. So I get r squared, which is equal to r squared. In other words, plugging these equations in, they work. Right? Now, let's twist it a little bit. What if I divide this by a squared? I tell you what, I'll write it over here. Yeah, fine. I'm tempted to overwrite this and make it different, but well, no, I'm going to do it here. It's the best way to do it. So if I divide this by a squared, right? And if I divide this by b squared, what do we have? Oh, I'm sorry. I won't do that. I won't do it. I'm sorry. I take it back. I take it back. Why, you should take notes in pencil. It's here. So sorry. What if I have, I see why I don't want to do that. X minus x1 squared plus y minus y1 squared equals to 1. And here I've got division by a squared. And here I've got division by b squared. Here a and b are positive. Right? This is what? This is an ellipse centered at x1, y1. All right? And you can read your chapter for more particulars on where the foci are and all that fun stuff. Semi-major, semi-minor axis, all those interesting things. As you may know, this is the set of points which are such that the sum of the distance between the two focal points is fixed and equal to a constant, right? So you take two points, and you can think about taking a loop of fixed length, right? And if you take a pencil and you draw a thing around, you'll get an ellipse. Okay. Anyway, I did that last year, but semester. I don't think it really added much to the lecture, so I'm just going to go on here. What's the parameterization of this? Well, it's almost the same thing, right? Almost the same thing, except what you do is you do x is equal to x1 plus r over a cosine t. And you do y is equal to y1 plus r over b sine t. This will work. Right? Now the reason this will work, and that's of course for 0 less than or equal to t less than or equal to 2 pi, sidebar, why does that work? Let's work it out over here. So here's the proof, so to speak. So x minus x1 is equal to what? R over a cosine t, right? Y minus y1 is equal to what? R over b sine t. Did I write b? Yeah, I did. Okay. So what's x minus x1 squared over a squared plus y minus y1 squared over b squared equal to? Well, what have I done?
You just write, there's no R in there, so I think it should be.
Oh, man. Yeah. Oh, stink. Yeah, if I put the R here, then I need that. I don't need it though, do I? Yeah, you're right. Fine, this. Oh, yes, you're right. Yeah, I was about to see why that doesn't work. Thank you. We'd find out very soon. See, if you had just give me about 30 seconds more, I would have cursed my own work. So I wasn't quite there yet, but yeah, it should be a cosine t, b sine t. Thank you. Okay, so this is why it's important to think through what you're doing and not just write down formulas from memory, right? It's true for me, it's true for you guys too. So Does this work? I mean, it definitely gels with what we have written in purple, because an ellipse is just a circle where the semi-major and semi-minor axes are both equal and the same, right? I mean, it's, or you can think of it as two focal points are the same point, namely the center of the circle. Okay, so here we get what? We get a cosine t squared over a squared plus b sine t squared over b squared, which is what? Cosine squared plus sine squared, which is 1, right? So that proves that these formulas land on the ellipse. Now, how do I know that they get the whole ellipse? That's more subtle, right? But that is verified by the fact that the sine and the cosine range over all possible positive and negative signs, right? Like the cosine is going from plus and minus, and the sine is going from plus and minus. And if you think back to our discussion about how sine and cosine change their signs, SIGNs, from quadrant to quadrant, you can convince yourself that this will hit every part of the ellipse by letting t cycle from 0 to 2 pi. I guess that's not a proof, but I will assure you that this does cover the ellipse. You'll forgive me if I don't prove it for you. Any questions about this? So if I give you guys specific numerical ellipses, you can parameterize them now? Because I do expect you to remember this, or like you need to internalize this one way or another. So like here's an example. Parameterize x squared plus 4x plus 6y squared equals to 1 for y less than or equal to 0. So I put a wrinkle in this, didn't I? So we have to do first what? That's x plus 2 quantity squared, right? And then minus 4 plus 6y squared equals to 1, which is x plus 2 quantity squared plus 6y squared is equal to 5. Or I suppose if you want to make it in the format, the standard format for an ellipse, we do what? Divide this by 5, divide that by 5. Well, fine, it's getting too busy. Let me write the next one. X plus 2 quantity squared over, well, weird, plus y squared over 5/6 equals to 1. So there you go. And now we have rewritten the curve so that it's a standard curve. We understand what this curve is. It's an ellipse, right? Where is its center? Minus 2, 0, and a is equal to the square root of 5, and b is equal to the square root of 5 over 6. Right? So now I just go to my standard toolbox, and I write down the parameterization. Parameterization here, x equals to the square root of 5 cosine t. Y is equal to the square root of 5 over 6 sine t. But there's something I'm ignoring, right? Here I have to be geometric. This is what? With y less than or equal to 0, right? So you think about what that means geometrically. So I don't know, this is just a rough sketch, right? Rough sketch of the ellipse. What do we want? We only want the y less than 0 piece, right? So we just want this stuff down here. So what should I do with my parameter range in order to make that be all that I get? Pi to 2, yeah, so if I could say pi less than or equal to t less than or equal to 2 pi, that'll do it. That's one of the choices. Or if you wanted, you could do minus pi less than or equal to t less than or equal to 0. That'd also be good. Yeah, choices. Yep.
Are you forgetting the minus 2 of the x?
Oh, yes, I am. Thank you. Very good point. So minus 2. Yeah. And if this problem was worth 10 points, that'd probably be about how many points I lost on that. Yeah. Everything else being the same. I mean, there's a lot of moving parts here, right? Like a student's got the right multiplier in front of cosine, they got the right multiplier in front of the sine. They've put the parameter range appropriate to the problem, and they just forgot to subtract the 2. I feel like that's like about a 20% deduction. Something like that. So, sorry. Yeah, for a 10-point question. Not putting the minus 2, I would take off 2 points. Yeah. So it's very appropriate. I'm sorry, it's too soon. I shouldn't talk about these things. Let's see here. So there's your ellipses. What are the other standard curves we know about? Well, by now you should have noticed a theme in here. We talk about sine and cosine, and we talk about what else? Cosh and sinh, right? Yeah, those are the other examples. So the other thing we might have is something like x minus x1 squared minus y1 squared equals to 1. And let me just go ahead and go straight to the ugly one. So over a squared over b squared. This would be a hyperbola. All right. And let me just, I know this is less familiar. I mean, you guys have seen ellipses and circles before, I think. I don't think I'm really telling you anything entirely new there, I hope. Show of hands, who has never seen a circle or ellipse equation presented in a math class before? I mean, there's no shame in it if it's the case. It's unfortunate, but it's no shame. You guys have all seen that before, right? How many people have seen this? A lot of people. Good. So I'm boring you then, I'm sorry. But so this would have center x1, y1, right? And what's it look like? Let me put x1 and y1 up here. So again, I'm assuming a and b are positive for the sake of us not going nuts. Let's see here. If you put x equal to x1, right, what happens? Think about this. X equals to x1, we've got minus y1, minus y minus y1 squared equals to 1. Is it possible to have a negative number equal to 1? It is not, right? So the curve does not pass the line x equals to 1, x equal to x1. So this is a, what kind of opening one? Here's your x equals to x1, right? So this is a hyperbola which opens sideways, all right? There's two branches, right? The one is like this, and the other one's over here like so. They're both asymptotically going to what, like, the asymptotes here, these guys, right? How do you find those? Basically, for asymptotes, x1 and y1 are irrelevant. And essentially, x wins, y wins, they're huge. So the equation, and 1 is also like stupidly small. So basically, you're looking at x squared over a squared minus y squared over b squared is equal to 0 asymptotically. In other words, you've got y squared is equal to b squared over a squared x squared. That is, y is equal to plus or minus b over a times x. Those are your asymptotes for this hyperbola. That's how to think of them intuitively. So they're there. That's just helpful for graphing. How do we parameterize this thing? Well, let me set our sights a little bit smaller. How do we parameterize the right branch of it? So let's just parameterize this piece over here. So I want this to be r of t, which will be x of t, y of t technically, all right? By the way, guys, this isn't a common abuse. Like, I wrote x equals this. So, some people would complain and say, that's not x, that is x of t. Actually, the people who are really pedantic would say, you can't use x there. You should use something else. Like, you should call this f of t, and you should call that one g of t. And I can't do it, guys. I'm sorry. So, if you'll forgive me, technically x is a function of time here, But this is a common abuse of notation, right? So, sometimes we write the of t to emphasize we're thinking of x as a function of the parameter time. And sometimes we just write x. It's not really a big deal. But anyway, over here, how do you find these? What are the parametric formulas here? Well, let me tell you what they are. Oh man, time flies when you're having fun, huh? Let's see here. So you're like, speak for yourself. See here, x is equal to x1, and you guessed it, a cosh t. The hyperbolic cosine, yes. And then y is equal to y1 plus b sinh t. Yes, indeed. And you can calculate, of course, x minus x1 squared plus y minus y1 squared divided by a squared divided by b squared. What's that give us? That gives us cosh squared minus sinh squared. But that's exactly 1. So that proves then that, in fact, these are the parametric formulas. These give you a parameterization of the right branch of the ellipse. So, and what's the range for here? And this is for t in the reals. As t goes to infinity, you go up here. As t goes to minus infinity, you go down there. Like that. What are the parametric formulas for over here? So here you go. These are the parametric formulas for the left branch of the hyperbola. And for specific examples, we might have to complete the square before we could actually see how to write these formulas down, right? Now, what's the other thing that could happen is you could have a hyperbola which did what? Which opened vertically, right? Yeah. And then we'd probably need to switch the roles of cosh and sinh. All right? But maybe we'll do that example tomorrow or something, all right? So these are your main examples: line, circle, hyperbolas. If you can do these three, you've got probably 80% of what I would throw at you covered. All right? So now I posted the solutions to, you can turn off the thing now. I posted the solutions to